Tonight, we're going to confront something that will completely shatter your understanding of how big things can get in the universe. You think you know what large means. You've seen images of galaxies, maybe even tried to wrap your mind around their scale. But there's a structure out there, a galaxy discovered just recently, that makes even the largest galaxies we knew about look small by comparison. It's so vast that if you could somehow travel at the speed of light, it would take you over 16 million years just to cross from one side to the other. And by the end of tonight, you're going to understand not just how impossibly large this galaxy is, but why its existence challenges everything we thought we knew about how galaxies grow and what limits their size. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. When you look up at the night sky, you're seeing the Milky Way from the inside. That faint band of light stretching across the darkness, that is our galaxy, our home. 100,000 light years from edge to edge, containing somewhere between 200 billion and 400 billion stars, along with the Sun, along with Earth, along with everything humanity has ever known. To give you some sense of what 100,000 light years means, imagine you could travel at the speed of light. You would be moving at 186,000 miles every single second. At that speed, you could circle Earth 7.5 times in 1 second. And yet, even at this incredible speed, it would take you 100,000 years to cross from one side of the Milky Way to the other. If you started this journey when modern humans first appeared on Earth, roughly 300,000 years ago, you would only be about 1/3 of the way across. The Milky Way is genuinely vast. From our perspective here on Earth, it is almost incomprehensibly large. And yet, as we are about to discover, it is actually quite small compared to the largest structures in the universe. For a very long time, people believed the Milky Way was the entire universe. Everything. There was nothing beyond it. In the early 1900s, astronomers debated whether fuzzy patches of light they could see through telescopes were a nebula within our galaxy or entirely separate galaxies beyond it. The Great Debate, as it became known, was settled in 1924 when Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to observe individual stars in what we now call the Andromeda galaxy. He proved definitively that Andromeda was far outside the Milky Way, a separate galaxy entirely, roughly 2.5 million light-years away. This discovery changed everything. The universe was suddenly far larger than anyone had imagined. The Milky Way was not alone. It was one galaxy among many. And as telescopes improved, astronomers discovered more and more galaxies. Thousands, then millions, then billions. And today, we estimate there are roughly 2 trillion galaxies in the observable universe, each one a massive collection of stars, gas, dust, and dark matter. And among these 2 trillion galaxies, sizes vary dramatically. Some galaxies are tiny, containing just a few million stars and spanning only a few thousand light years, These are called dwarf galaxies, and they are actually the most common type in the universe. Most galaxies are small. Then there are galaxies like the Milky Way, large spiral galaxies containing hundreds of billions of stars. These are less common, but still fairly ordinary in the grand cosmic scheme. And then there are the giants, galaxies so enormous that they dwarf even large spirals like the Milky Way. Galaxies that contain not billions, but trillions of stars. Galaxies that stretch not for 100,000 light years, but for millions of light years. These are the true monsters of the cosmos, and the biggest one we have ever found is called Alcyonius. Now, before we dive into Alcyonius specifically, let me give you some context about what we are dealing with here. Throughout the history of astronomy, as our telescopes have improved, we have consistently found that the universe is larger and more complex than we previously thought. Every time we build a more powerful telescope, we discover structures that dwarf what we knew before. In the 1920s, when Hubble proved that Andromeda was a separate galaxy, the largest known structures were galaxy groups containing a few dozen galaxies. By the 1950s, astronomers had discovered galaxy clusters containing thousands of galaxies. By the 1980s, they had mapped superclusters containing thousands of clusters. And by the 2000s, they had discovered great walls, enormous filaments of galaxies stretching hundreds of millions of light years. Each discovery pushed the limits of what we thought possible, and Alcyonius is the latest in this series of discoveries, a structure that redefines our understanding of how large a single galaxy can be. Before we get to Alcyonius, we need to understand what makes a galaxy big. Because size in astronomy is not always straightforward. When we talk about a galaxy's size, we are usually talking about the diameter of its visible structure, the region where most of its stars are located. For the Milky Way, that is about 100,000 light years. But galaxies are not solid objects with sharp edges. They fade gradually at their boundaries, becoming less and less dense until you cannot really say where the galaxy ends and intergalactic space begins. Some galaxies also have extended structures that go far beyond their main bodies. These structures, called radiolobes, are created by supermassive black holes at the centers of galaxies. When matter falls into these black holes, it does not all get swallowed. Some of it gets accelerated to nearly the speed of light and shot out in two opposite directions as jets of particles and energy. These jets can extend for millions of light years beyond the galaxy itself. The particles in the jets interact with magnetic fields and emit radio waves, which is how we detect them. These radiolobes can make a galaxy's total size much, much larger than the visible galaxy alone. To understand how radiolobes form, we need to talk about supermassive black holes and accretion disks. Every large galaxy has a supermassive black hole at its center. The one at the center of the Milky Way, called Sagittarius A, has a mass of about 4 million times the mass of the Sun. That might sound enormous, and it is by human standards, but it is actually quite small for a supermassive black hole. Some black holes at the centers of galaxies have masses of billions or even tens of billions of solar masses. Most of the time, these black holes are quiet. They are not actively feeding on material, so they produce very little radiation. But sometimes, gas and dust from the surrounding galaxy falls toward the black hole. As this material spirals inward, it forms an accretion disk, a flat disk of matter orbiting the black hole at tremendous speeds. The particles in the disk are moving so fast and are packed so tightly that friction heats them to millions of degrees. At these temperatures, the disk glows brilliantly across the electromagnetic spectrum, from radio waves to X-rays. The brightest active galactic nuclei can outshine all the stars in their host galaxies combined. We are talking about a region no larger than our solar system, producing more light than hundreds of billions of stars. But not all the material in the accretion disk falls into the black hole. Some of it gets caught up in the black hole's magnetic field. Black holes themselves do not have magnetic fields, but the swirling plasma in the accretion disk does. This plasma is composed of ionized gas that has been heated so much that electrons have been stripped away from atoms, leaving charged particles. These charged particles interact with magnetic fields, and as they spiral around the field lines, they can be accelerated to tremendous speeds. Near the poles of the black hole, where the magnetic field lines are most concentrated, some of this material gets funneled into narrow jets. These jets shoot outward in opposite directions perpendicular to the accretion disk. The particles in the jets are moving at 99% of the speed of light, or faster. At these relativistic speeds, the normal laws of physics start behaving strangely due to Einstein's theory of relativity. Time slows down for the particles, distances contract, and the energy carried by the jets becomes truly enormous. A single jet from an active galactic nucleus can carry more energy than 1 billion supernovae. These jets plow through the intergalactic medium, the thin gas that exists between galaxies. Now, with that background, let me tell you about Alcyonius. Alcyonius is one of these galaxies. It is a giant elliptical galaxy located roughly 3 billion light-years from Earth in the constellation Lynx. The galaxy itself, the main body containing most of its stars, is large, but not exceptionally so. It is about 660,000 light-years across, roughly 6.5 times the diameter of the Milky Way. That is big, but there are other galaxies with larger main bodies. What makes Alcyonius special? What makes it the biggest galaxy we have ever discovered are its radio lobes. The jets from Alcyonius's central black hole have created 2 enormous lobes extending in opposite directions from the galaxy. These lobes stretch for 16.3 million light-years from end to end. 16.3 million light-years. To put that in perspective, the Milky Way is 100,000 light-years across. Alcyonius is 163 times longer. If the Milky Way were the size of a grain of rice, Alcyonius would be the length of a football field. Actually, longer than a football field, more like the length of a city block. The Andromeda galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. Alcyonius is more than 6 times longer than the distance between the Milky Way and Andromeda. If Alcyonius were positioned with one end at the Milky Way, the other end would extend far beyond Andromeda, past the entire local group of galaxies, reaching into the space between galaxy groups. This is a structure so vast, it challenges comprehension. Light itself, traveling at 186,000 miles per second, takes 16.3 million years to cross from one end of Alcyonius to the other. If you started at one end and could somehow travel at the speed of light, by the time you reached the other end, 16.3 million years would have passed. For context, 16.3 million years ago on Earth, our human ancestors had not yet appeared. The earliest hominins would not evolve for another 10 million years. The continents were still in different positions. The climate was completely different. And light that left one end of Alcyonius back then is only now reaching the other end. Now, you might be wondering how such a structure can even exist. How can jets of particles travel millions of light-years through space? What prevents them from dispersing or being disrupted? The answer has to do with the power of the central black hole and the nature of the intergalactic medium. The supermassive black hole at the center of Alcyonius is feeding on gas and dust from the surrounding galaxy. As matter spirals into the black hole, it forms an accretion disk, a swirling disk of material orbiting the black hole at tremendous speeds. The friction in this disk heats the material to millions of degrees, causing it to emit intense radiation. Some of this material does not fall into the black hole. Instead, it gets channeled along the black hole's magnetic field lines and accelerated to nearly the speed of light. This creates two narrow jets shooting out in opposite directions perpendicular to the accretion disk. These jets are incredibly powerful. The energy output from an active galactic nucleus like this can exceed the energy output of all the stars in the galaxy combined. We are talking about energies that dwarf anything we encounter in normal stellar processes. The jets plow through the intergalactic medium, the thin gas that exists between galaxies. As they do, they push this gas aside, creating vast bubbles. These bubbles are the radio lobes we observe. The particles in the jets are mostly electrons and protons, moving at relativistic speeds. When these particles interact with magnetic fields in the intergalactic medium, they emit synchrotron radiation, which we detect as radio waves. This is how we know the lobes are there. They are invisible to optical telescopes, but they glow brightly at radio wavelengths. What is remarkable is that the jets can remain coherent and focused across such enormous distances. You might think that a jet of particles would spread out and dissipate over millions of light-years, but the magnetic fields associated with the jets help keep them collimated, preventing them from spreading too much. The jets from Alcyonius have been active for a very long time. To create lobes this large, the black hole must have been actively feeding and producing jets for tens of millions of years at least, possibly hundreds of millions of years. This is a timescale that is hard to grasp. Human civilization is only a few thousand years old.
Our species has existed for only a few 100,000 years. The jets from Alcyonius have been streaming across space for a duration that makes the entire history of humanity look like an eye blink. Alcyonius was discovered in 2021 by a team of astronomers led by Martijn Y at Leiden University in the Netherlands. They found it by analyzing data from the LOFAR radio telescope, the low-frequency array, which is specifically designed to detect the kind of low-frequency radio emissions produced by these giant radio lobes. The discovery was somewhat serendipitous. Alcyonius was not particularly bright or prominent in radio observations. It was just one of many radio galaxies in the survey data. But when the team measured the full extent of its lobes, they realized they had found something extraordinary. At the time of its discovery, Alcyonius broke the previous record for the largest known galaxy structure. That record had been held by another radio galaxy with lobes extending about 15 million light-years. Alcyonius is about 8% larger, which might not sound like much, but at this scale, even a small percentage difference represents hundreds of thousands of light-years. What makes this discovery particularly interesting is that Alcyonius is not exceptionally massive or bright. The galaxy itself is fairly typical for a giant elliptical. Its central black hole is large, probably around 400 million times the mass of the Sun. But that is not unusually large for galaxies of this type.
Some supermassive black holes are billions of times the mass of the Sun. So why did Alcyonius grow so large? The answer seems to be a combination of factors. First, the galaxy is located in a relatively low-density environment. The intergalactic medium around it is thinner than average, which means the jets encounter less resistance as they expand. In denser environments, jets are more likely to be disrupted or compressed by the surrounding gas. Second, Alcyonius appears to have been producing jets steadily for a very long time, without major interruptions. Many active galactic nuclei go through cycles where the jets turn on and off as the black hole's feeding rate changes. Alcyonius seems to have maintained a relatively constant output, allowing the lobes to grow continuously. Third, the orientation of the galaxy may play a role. The jets happen to be oriented in a direction where there are no major structures to block or deflect them. They have had a clear path through space for millions of light-years. It is also worth noting that Alcyonius is not unique in having massive radio lobes. There are other radio galaxies with lobes extending millions of light-years. Alcyonius is simply the largest we have found so far. As our radio telescopes improve and we survey more of the sky, we may discover even larger structures. In fact, there is no fundamental physical limit preventing radio lobes from growing even larger than this. The main limitations are the longevity of the jets and the density of the surrounding environment. A galaxy in an even emptier region of space, with jets that have been active even longer, could potentially have lobes stretching 20 million light-years or more. Now let me explain in more detail what these radio lobes actually are and how they maintain their structure over such vast distances. The lobes are not solid objects. They are regions of space filled with high-energy particles and magnetic fields. When the jets from the central black hole shoot out into space, they are carrying electrons and other charged particles moving at 98 or 99% of the speed of light. These are called relativistic speeds, speeds where the effects of Einstein's special theory of relativity become significant. At relativistic speeds, strange things happen. Time slows down for the moving particles compared to stationary observers. The particles' mass effectively increases, and the energy they carry becomes enormous. As these relativistic particles plow into the intergalactic medium, they create a shock wave, like the bow wave of a ship moving through water. Behind this shock, a bubble forms, filled with the particles from the jet. This bubble is the radiolobe. The particles in the lobe are trapped by magnetic fields. As they spiral around these magnetic field lines, they emit synchrotron radiation. Synchrotron radiation is electromagnetic radiation produced when charged particles are accelerated in a magnetic field. The frequency of the radiation depends on the strength of the magnetic field and the energy of the particles. In the case of radiolobes, the particles are so energetic and the magnetic fields are strong enough that the synchrotron radiation is produced at radio wavelengths. This is why we call them radiolobes. They glow brightly at radio frequencies, even though they are invisible to optical telescopes. Over time, the particles in the lobes lose energy. As they emit synchrotron radiation, they slow down. This means that radiolobes fade over time. If the jets shut off and stop supplying fresh, high-energy particles, the lobes will gradually dim and eventually become undetectable. The fact that Alcyonius's lobes are still bright means the jets are still active, still pumping energy into the lobes. This is happening right now, even as we speak. Or rather, it was happening 3 billion years ago when the light we are now observing left Alcyonius. The pressure inside the lobes is higher than the pressure in the surrounding intergalactic medium. This pressure difference helps keep the lobes inflated like a balloon. If the pressure inside dropped, the lobes would collapse. But as long as the jets keep supplying energy and particles, the pressure remains high enough to maintain the structure. One of the fascinating aspects of radio galaxies is that the lobes can tell us about the history of the jet activity. Sometimes you can see multiple lobes or complex structures that indicate the jets have turned on and off multiple times, or that the direction of the jets has changed. In Alcyonius, the lobes appear relatively smooth and symmetric, suggesting steady, continuous jet activity. But in other radio galaxies, the lobes show knots, bends, and irregularities that reveal a more turbulent history. Radio lobes can also interact with their environment in interesting ways. If a lobe expands into a region where the intergalactic medium is denser, it will slow down and may even be compressed. If it expands into a void where the medium is especially thin, it can grow more rapidly. The shape and extent of radio lobes therefore provide clues about the structure of the intergalactic medium, which is otherwise difficult to study because it is so diffuse. Alcyonius's enormous lobes tell us that it has been fortunate enough to expand into a particularly empty region of space. If it were in a denser environment, the lobes would be smaller, compressed by the surrounding gas. But in its sparse neighborhood, the lobes have been free to grow to record-breaking sizes. This makes Alcyonius not just a curiosity, but a valuable tool for understanding the intergalactic medium and the physics of relativistic jets.
By studying Alcyonius and other radio galaxies, astronomers can learn about some of the most extreme phenomena in the universe. Supermassive black holes, relativistic jets, magnetic fields, and the near-empty spaces between galaxies. A galaxy in an even emptier region of space, with jets that have been active even longer, could potentially have lobes stretching 20 million light-years or more.
But before we go any further, let us talk about other enormous galaxies. Because Alcyonius is not the only giant out there. When we talk about the biggest galaxies by their main stellar bodies, rather than their radio lobes, different galaxies take the title. The largest galaxy by stellar extent is IC 1101. This is a supergiant elliptical galaxy located about 1.07 billion light-years away in the constellation Virgo. IC 1101 is approximately 6 million light-years across. That is 60 times the diameter of the Milky Way. If IC 1101 were positioned where the Milky Way is, it would stretch far beyond Andromeda. The entire local group of galaxies, which includes the Milky Way, Andromeda, Triangulum, and dozens of smaller galaxies, would fit inside IC 1101 with room to spare. This galaxy contains roughly 100 trillion stars. For comparison, the Milky Way has between 200 billion and 400 billion stars. IC 1101 has about 250 times more stars than the Milky Way. Think about that. Every star you see in the night sky, every constellation, every nebula observed by telescopes, all of it is contained within the Milky Way. Now imagine a galaxy with 250 times more stars. The sheer number becomes almost meaningless, because our brains cannot really grasp what 100 trillion stars looks like. IC 1101 did not start out this large. It grew through a process called galactic cannibalism. The galaxy sits at the center of a galaxy cluster called Abell 2029. Galaxy clusters are violent places where galaxies regularly pass close to each other. When they do, the larger galaxy's gravity can strip stars away from smaller galaxies. Over billions of years, a galaxy at the center of a cluster can consume dozens or even hundreds of smaller galaxies, growing larger and larger with each merger. IC 1101 has been doing this for billions of years. It is the gravitational bully of its neighborhood, pulling in any galaxy that comes too close. The result is a bloated, enormous, elliptical galaxy packed with stars. The process of galaxy cannibalism is both violent and beautiful when viewed on cosmic timescales. When a smaller galaxy approaches IC 1101, it does not crash into it like two cars colliding. Instead, gravity does the work. As the smaller galaxy gets closer, IC 1101's gravity begins to pull stars away from it. The outer regions of the smaller galaxy are pulled harder than the core because they are closer to IC 1101. This creates tidal forces, the same type of forces that cause ocean tides on Earth, just on a vastly larger scale. These tidal forces stretch the smaller galaxy, pulling it into long streamers of stars. Eventually, these streams wrap around IC 1101 and over hundreds of millions of years, the orbits of the captured stars are randomized. They become part of IC 1101's stellar population, indistinguishable from stars that were there originally. The smaller galaxy effectively disappears, absorbed entirely into the giant. And IC 1101 has done this not once or twice, but dozens or perhaps hundreds of times. Every dwarf galaxy that wandered too close got consumed. Every smaller elliptical that strayed into IC 1101's gravitational influence got torn apart and absorbed. Over billions of years, all those consumed galaxies added up, building IC 1101 into the supergiant it is today. The interesting thing is that this process is still happening. IC 1101 is still consuming galaxies right now. If we could watch it for a few 100 million years, we would see new tidal streams forming as fresh galaxies are torn apart. We would see IC 1101 growing larger with each merger. Galaxy cannibalism is not unique to IC 1101. It happens throughout the universe, wherever galaxies interact. The Milky Way itself is consuming several smaller galaxies right now. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way's gravity. Its stars are being stripped away and incorporated into our galaxy's halo. The Canis Major dwarf galaxy is undergoing the same fate. Even the Large Magellanic Cloud and the Small Magellanic Cloud, two of our nearest galactic neighbors, will eventually be consumed by the Milky Way. In about 2.5 billion years, the Large Magellanic Cloud will collide with the Milky Way, and its stars will become part of our galaxy. So the process that built IC 1101 into a giant is the same process that the Milky Way is engaging in right now, just on a smaller scale. The difference is that IC 1101 sits at the center of a rich galaxy cluster where interactions are far more common. The Milky Way is in a relatively sparse region of space, so it encounters smaller galaxies less frequently. If the Milky Way were in IC 1101's position, it too might have grown into a supergiant by now. Location matters in galaxy evolution. Galaxies in dense environments grow faster because they have more neighbors to consume. Galaxies in sparse environments grow more slowly because encounters are rare. If you were somehow standing on a planet near the center of IC 1101, your night sky would be incredible. The density of stars near the galaxy's core is thousands of times higher than in the Milky Way. You would see stars in every direction, many of them close enough to shine as brightly as Venus or Jupiter appear in our sky. There would be no dark patches, no empty spaces. The entire sky would glow with starlight. Constellations would be meaningless because individual stars would be impossible to distinguish. The sky would be a nearly continuous wash of light. But IC 1101 is not the only supergiant elliptical. There is M87, located in the Virgo cluster, about 53 million light-years away. M87 is a fascinating galaxy for multiple reasons, and it deserves a closer look because it represents another extreme in the universe. M87 is roughly 120,000 light-years across, similar in diameter to the Milky Way, but it contains about 1 trillion stars, roughly 3 to 5 times more than the Milky Way. The galaxy is classified as a supergiant elliptical, and it sits at the heart of the Virgo cluster, dominating its surroundings. But what makes M87 truly famous is its supermassive black hole. In April 2019, the Event Horizon Telescope collaboration made history by releasing the first ever direct image of a black hole's event horizon. That black hole was the one at the center of M87. The image showed a bright ring of glowing gas surrounding a dark central region, the black hole's shadow. It was a triumph of observational astronomy, confirming decades of theoretical predictions about what black holes should look like. The black hole at the center of M87 has a mass of about 6.5 billion times the mass of the Sun. To put that in perspective, the black hole at the center of the Milky Way, Sagittarius A, has a mass of only about 4 million solar masses. M87's black hole is over 1,600 times more massive. This enormous black hole has an event horizon, the boundary beyond which nothing can escape, that is about 23.6 billion miles across. That is roughly 250 times the distance from the Sun to Earth. If you placed this black hole at the center of our solar system, its event horizon would extend far beyond the orbit of Neptune, engulfing all the planets. The event horizon defines the point of no return. Once anything crosses this boundary, whether matter or light, it can never escape. The gravity is so strong that the escape velocity exceeds the speed of light. And since nothing can move faster than light, nothing can get out. The ring of light in the Event Horizon Telescope image is not the event horizon itself. It is the photon ring, a region just outside the event horizon where light orbits the black hole before either escaping or falling in. This light comes from the accretion disk, the swirling disk of superheated gas orbiting the black hole. The dark region in the center of the image is larger than the event horizon itself. It is the black hole's shadow, which includes both the event horizon and a region around it where light is so strongly bent by gravity that it falls into the black hole. Creating this image required an extraordinary international effort. The Event Horizon Telescope is not a single telescope, but a global network of radio telescopes working together. By combining observations from telescopes in locations around the world, from Hawaii to Chile to Antarctica, astronomers created an effective telescope the size of Earth. This technique, called Very Long Baseline Interferometry, allowed them to achieve the angular resolution needed to see details as small as the event horizon of M87's black hole. Even with an Earth-sized telescope, M87's black hole only appears as a tiny speck in the sky. The angular size is about 40 micro-arcseconds. To understand how small that is, imagine looking at a donut on the surface of the moon. That is roughly the angular size of M87's black hole shadow as seen from Earth. The fact that we can resolve such a small feature from 53 million light-years away is a testament to the power of modern observational techniques. M87 is also a powerful radio source. Like Alcyonius, M87 has jets produced by its supermassive black hole. These jets are not as large as Alcyonius's, extending only about 5,000 light-years from the galaxy, but they are still enormous by any reasonable standard. 5,000 light-years is 50 times the distance from Earth to the nearest star after the Sun. The jets from M87 move at relativistic speeds, just like those from Alcyonius. Matter in the jets travels at more than 98% the speed of light. These jets are some of the fastest phenomena in the universe, and they carry enormous amounts of energy away from the black hole. The power output of M87's jets is difficult to comprehend. They are releasing energy at a rate that exceeds the total power output of all the stars in the Milky Way. And this energy comes from a region no larger than our solar system. The central engine, the supermassive black hole and its accretion disk, is incredibly compact compared to the galaxy as a whole. But it outshines hundreds of billions of stars. One of the mysteries about supermassive black holes is how they grew so large. 6.5 billion solar masses is an incredible amount of mass to accumulate. If the black hole at the center of M87 grew by consuming matter at the maximum possible rate, called the Eddington limit, it would still take billions of years to reach its current mass. And yet we know that supermassive black holes existed when the universe was very young, less than 1 billion years old. Some of these early black holes already had masses of billions of solar masses. How did they grow so fast? This is one of the major unsolved questions in astrophysics. There are several theories. Perhaps supermassive black holes started from seeds that were already quite massive, maybe hundreds or thousands of solar masses, rather than growing from stellar mass black holes. Or perhaps in the early universe, black holes could grow faster than the Eddington limit under certain conditions. Or perhaps multiple black holes merged together in the dense cores of early galaxies, rapidly building up mass. The truth is, we do not fully understand how supermassive black holes formed and grew. And galaxies like M87, with their enormous central black holes, are key to unraveling this mystery. M87 has another claim to fame. It is one of the brightest sources of X-rays in the sky. X-rays are produced by gas that has been heated to millions of degrees. In M87, this hot gas fills the space around the galaxy, forming what is called a hot gaseous halo. This halo contains as much mass as all the stars in the galaxy combined. It is held in place by the gravity of M87 and the dark matter halo surrounding the galaxy. The hot gas in this halo glows brightly at X-ray wavelengths, making M87 easily detectable by X-ray telescopes. Studying this hot gas tells us about the history of the galaxy. The gas was heated by supernova explosions and by energy from the central black hole's jets. Over billions of years, these processes have pumped enormous amounts of energy into the gas, keeping it hot and preventing it from cooling and forming new stars. This is why M87, like most elliptical galaxies, is not forming many new stars. The gas is too hot to collapse and ignite star formation. In this sense, the black hole is regulating the galaxy's growth. By heating the surrounding gas, it prevents new stars from forming, which in turn reduces the amount of gas that can eventually fall into the black hole. It is a form of feedback where the black hole's activity affects its own food supply. Understanding this feedback process is crucial to understanding how galaxies evolve. And M87, with its powerful black hole and well-studied hot gas halo, is one of the best laboratories for studying these processes. So while M87 might not have the largest stellar extent among galaxies, it is nevertheless an extreme object. Its supermassive black hole is one of the most massive known. Its jets carry incredible amounts of energy. Its hot gas halo glows brightly at X-rays, and it was the first galaxy where we directly imaged a black hole's event horizon. M87 represents the upper end of what black holes and their host galaxies can become. Then there is A2261-BCG, located about 3 billion light-years away at the center of the galaxy cluster Abell 2261. This galaxy is roughly 2 million light-years across, 20 times the diameter of the Milky Way. It contains an estimated 10 trillion stars. Again, these numbers start to lose meaning. 10 trillion stars? What does that even look like? If you tried to count to 10 trillion, counting one number per second without stopping, it would take you over 300,000 years. These supergiant galaxies are among the most massive objects in the universe. They represent the upper end of galaxy sizes, the absolute largest structures that gravity can hold together. But here is something crucial to understand. These galaxies are rare, extremely rare. Out of the 2 trillion galaxies in the observable universe, only a tiny fraction are supergiants like IC 1101 or A2261-BCG. Most galaxies are much smaller. In fact, the vast majority of galaxies are dwarf galaxies, small structures containing just a few million to a few billion stars and spanning only a few thousand light-years. Let me give you some specific examples to drive this point home. The Segway 1 galaxy is one of the smallest known galaxies. It contains only about 1,000 stars, and it is just a few hundred light-years across. That is barely a galaxy at all. It is more like a large star cluster. Segway 1 orbits the Milky Way as a satellite galaxy, held in orbit by our galaxy's gravity. And there are dozens of galaxies like Segway 1 orbiting the Milky Way. Tiny, faint, containing very few stars. The Large Magellanic Cloud, one of our nearest galactic neighbors, visible to the naked eye from the southern hemisphere, contains about 10 billion stars. That sounds like a lot, and it is, but it is only about 2 to 5% of the number of stars in the Milky Way. The Large Magellanic Cloud is about 14,000 light-years across, roughly 1/7 the diameter of the Milky Way. It is a substantial galaxy, but it is dwarfed by the Milky Way. The Small Magellanic Cloud is even smaller, containing only about 3 billion stars and spanning about 7,000 light-years. And these are among the larger dwarf galaxies. Most dwarf galaxies are much smaller and fainter than the Magellanic Clouds. The Ursa Major 1 dwarf galaxy contains only about 10,000 stars. The Draco dwarf spheroidal galaxy contains about 400,000 stars. The Sculptor dwarf galaxy contains about a few million stars. All of these are satellites of the Milky Way, orbiting around us, held in place by gravity.
And this pattern repeats throughout the universe. Every large galaxy is surrounded by dozens or even hundreds of dwarf galaxies. Andromeda has its own collection of satellite galaxies. M87 has dozens of dwarfs orbiting it. Wherever there is a large galaxy, there are many small ones nearby. Dwarf galaxies are by far the most common type of galaxy in the universe. If you randomly selected 1,000 galaxies from across the cosmos, probably 900 or more would be dwarfs. Only a small minority would be large spirals like the Milky Way or large ellipticals like M87. And only a tiny fraction would be supergiants like IC 1101. This is important to understand because it puts the Milky Way's size into proper context. When most people hear about giant galaxies like IC 1101, they often come away thinking that the Milky Way is small, and compared to IC 1101, it is. But IC 1101 is exceptionally rare. It is an outlier, not the norm. The typical galaxy is far smaller than the Milky Way. Most galaxies would look up at the Milky Way with envy, if galaxies could have feelings. The Milky Way, with its 100,000 light-year diameter and hundreds of billions of stars, is actually quite large compared to most galaxies. If you randomly selected 1,000 galaxies from the universe, probably 950 of them would be smaller than the Milky Way. Maybe 40 would be roughly similar in size, and only about 10 would be larger, with just 1 or 2 being dramatically larger, like IC 1101. The Milky Way is not in the top 1% of galaxy sizes, but it is comfortably in the top 5%. That makes it large, genuinely large by cosmic standards. We are not living in some tiny, insignificant corner of the universe. Our galaxy is one of the bigger ones that exist. But compared to the absolute giants, the IC 1101s and the Alcyoniuses, the Milky Way is small. Not tiny, not insignificant, but definitely small. And when we zoom out even further, when we look at structures larger than individual galaxies, the Milky Way becomes even smaller in comparison. Galaxies are not randomly scattered through space. They cluster together due to gravity. The Milky Way is part of a small cluster called the Local Group, which contains about 50 galaxies. Most of these are dwarf galaxies. The only large galaxies in the Local Group are the Milky Way, Andromeda, and the Triangulum galaxy. The entire Local Group spans about 10 million light-years across. That might sound enormous, and by human standards it certainly is. But in cosmic terms, it is just a small cluster. There are galaxy clusters that are much, much larger. The Virgo cluster, for example, is one of our nearest large galaxy clusters.
It sits about 53 million light-years away and contains somewhere between 1,300 and 2,000 galaxies. The Virgo cluster spans about 15 million light-years across. At its center sits M87, the giant elliptical galaxy we talked about earlier. M87 dominates the Virgo cluster, its gravity holding the cluster together. The Coma cluster is even larger, containing over 1,000 large galaxies and potentially tens of thousands of smaller dwarf galaxies. It spans about 20 million light-years across and sits about 320 million light-years from Earth. The Coma cluster is one of the densest concentrations of galaxies we know of. In regions like the Coma cluster core, galaxies are packed so tightly that collisions and interactions are common. This is where giant elliptical galaxies like IC 1101 form, growing large by consuming their neighbors. But galaxy clusters are not the end of the story. Clusters themselves group together into superclusters. The local group is part of a much larger structure called the Virgo supercluster. The Virgo supercluster contains about 100 galaxy groups and clusters, including the massive Virgo cluster, which gives the supercluster its name. The Virgo supercluster spans about 110 million light-years. To put that in perspective, light takes 110 million years to cross from one side of the Virgo supercluster to the other. 110 million years ago, on Earth, dinosaurs were still tens of millions of years away from evolving. The first mammals were small, shrew-like creatures. The continents were arranged differently than they are today. And light, leaving one edge of the Virgo supercluster back then, is only now reaching the opposite edge. The local group is not particularly special. We are on the outskirts, in a relatively sparse region. The action, the dense concentrations of galaxies, the massive clusters, those are all closer to the center, near the Virgo cluster itself. We are suburbanites in the cosmic landscape. But even the Virgo supercluster is part of something larger. In 2014, astronomers published a study that redefined our understanding of large-scale structure. Using data from thousands of galaxies, they mapped out the flow of galaxies through space. Galaxies are not stationary. They are moving, pulled by the gravity of surrounding mass. By analyzing these motions, the researchers discovered that the Virgo supercluster is actually part of an even larger structure. They called it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster, a collection of multiple superclusters, all flowing toward a common gravitational center. It spans approximately 520 million light-years and contains roughly 100,000 galaxies. Think about that for a moment. 100,000 galaxies, each containing millions, billions, or even trillions of stars, all of them bound together, however loosely, by gravity, into a single, vast structure. The Milky Way is one tiny piece of Laniakea, one galaxy among 100,000. At the heart of Laniakea is a region of space called the Great Attractor. The Great Attractor is a massive concentration of mass, probably composed of multiple galaxy clusters, that is pulling everything in the Laniakea supercluster toward it.
The Milky Way is moving toward the Great Attractor at a speed of about 373 miles per second. That is over 1.34 million miles per hour. We are racing through space at incredible speed, pulled by the gravity of a structure we can barely see because it lies behind the plane of our own galaxy, hidden by dust and gas. The discovery of the Great Attractor was one of the great mysteries of astronomy in the 1970s and 80s. Astronomers could measure the motion of galaxies and determine that something massive was pulling us, but they could not see what it was. The region lies in what is called the zone of avoidance, an area of sky blocked by the Milky Way's disk.
Only in recent decades, using X-rays, infrared, and radio waves that can penetrate the dust, have astronomers been able to map out the Great Attractor and understand what is pulling us. It turns out to be a combination of several massive galaxy clusters, including the Norma cluster, along with even larger structures beyond, like the Shapley supercluster. The Shapley supercluster sits about 650 million light-years away and contains over 8,000 galaxies. It is one of the most massive structures in the nearby universe, and its gravity is strong enough to influence the motions of galaxies hundreds of millions of light-years away. Even Mauna Kea itself is being pulled toward the Shapley supercluster. At every scale, there is always something larger. Within Mauna Kea, the Milky Way is nothing special. It is one galaxy among 100,000, a single grain of sand on a beach. And Mauna Kea itself is just one supercluster among many. The universe is filled with these enormous structures, superclusters separated by vast voids, empty regions of space where very few galaxies exist. At the largest scales, the universe looks like a cosmic web. Filaments of galaxies stretching across hundreds of millions or even billions of light-years, connected by threads and separated by enormous voids. There is the Sloan Great Wall, a structure discovered in 2003 that stretches about 1.37 billion light-years across. It is a wall of galaxies, a sheet of matter extending across more than 1 billion light-years of space. If the Milky Way were the size of a grain of rice, the Sloan Great Wall would be longer than 10 football fields placed end to end. Then there is the Hercules Corona Borealis Great Wall, discovered in 2013. This structure is even larger, spanning about 10 billion light-years. 10 billion light-years. That is about 1/10 the diameter of the observable universe. The Hercules Corona Borealis Great Wall is so large that light takes 10 billion years to cross it. For perspective, the universe itself is only 13.8 billion years old. This structure formed when the universe was quite young, and it has been growing ever since. Structures like these challenge our understanding of how the universe formed. According to cosmological models, there should be a limit to how large structures can grow. The universe has only been around for 13.8 billion years, and gravity can only pull matter together so fast. Structures above a certain size simply should not have had enough time to form. And yet, here is the Hercules Corona Borealis Great Wall, seemingly violating that limit. Astronomers are still trying to understand how such enormous structures can exist. It may require revisions to our models of how the universe evolved in its early stages. Or it may suggest that our understanding of dark matter and dark energy the invisible components that make up most of the universe's mass and energy, is incomplete. The point is, at every scale we look, the universe reveals structures larger than we expected. Alcyonius is the largest single galaxy structure we have found, with its radio lobes extending 16.3 million light-years. IC 1101 is the largest galaxy by stellar extent, spanning 6 million light-years. Laniakea is the supercluster we inhabit, stretching 520 million light-years. The Sloan Great Wall is a filament of galaxies extending 1.37 billion light-years, and the Hercules Corona Borealis Great Wall spans 10 billion light-years. Each of these structures dwarfs the Milky Way. Each one makes our galaxy look small, insignificant, ordinary. And yet, the Milky Way is still home. It is still the galaxy that contains the Sun, the Earth, and us. Now, you might be wondering how astronomers measure these enormous distances. How do we know that Alcyonius is 3 billion light-years away? How do we know that IC 1101 is 1.07 billion light-years distant? You cannot just stretch a ruler from here to Alcyonius or IC 1101. The distances are far too large for any direct measurement. Instead, astronomers use a series of techniques collectively called the cosmic distance ladder. Think of it like a ladder, where each rung allows you to measure slightly greater distances, and you need to climb the lower rungs to reach the higher ones. The first rung of the ladder is parallax. This is the most direct method for measuring distances to nearby stars. Parallax works like this. Hold your finger up at arm's length and close one eye. Note where your finger appears against the background. Now open that eye and close the other one. Your finger appears to shift against the background. This shift happens because your two eyes are viewing your finger from slightly different positions. The same principle works for measuring distances to stars. As Earth orbits the Sun, we view nearby stars from different positions 6 months apart. A nearby star will appear to shift slightly against the background of more distant stars. By measuring this shift and knowing the size of Earth's orbit, we can use basic trigonometry to calculate the distance to the star. The European Space Agency's Gaia satellite has used parallax to measure distances to over 1 billion stars with incredible precision. But parallax only works for relatively nearby stars, those within a few thousand light-years. Beyond that, the shifts become too small to measure accurately. For greater distances, we need the second rung of the ladder: standard candles. A standard candle is any object whose intrinsic brightness is known. If you know how bright something actually is, and you can measure how bright it appears from Earth, you can calculate how far away it must be. It is like seeing a light bulb in the distance. If you know it is a 100-watt bulb, you can estimate its distance based on how bright it appears. One of the most important standard candles is the Cepheid variable star. Cepheid variables are stars that pulsate, growing brighter and dimmer in a regular cycle. Henrietta Swan Leavitt discovered in the early 1900s that there is a direct relationship between a Cepheid's pulsation period and its intrinsic brightness. A Cepheid that pulsates with a longer period is intrinsically brighter than one with a shorter period. This discovery was revolutionary because it meant that by simply measuring a Cepheid's pulsation period, you could determine its true brightness. And once you know its true brightness and measure its apparent brightness as seen from Earth, you can calculate its distance. Edwin Hubble used Cepheid variables to measure the distance to Andromeda in 1924, proving it was far outside the Milky Way. The Hubble Space Telescope has observed Cepheids in galaxies up to about 100 million light-years away. For even greater distances, we need an even brighter standard candle. That is where Type 1a supernovae come in. A Type 1a supernova occurs when a white dwarf star in a binary system accretes matter from its companion until it reaches a critical mass. At about 1.4 times the mass of the Sun, the white dwarf can no longer support itself, and it explodes catastrophically. The remarkable thing about Type 1a supernovae is that they all reach approximately the same peak brightness, because they all explode at the same critical mass. This makes them incredibly useful as distance markers. Type 1a supernovae are so bright that they can be seen billions of light-years away. They outshine entire galaxies for a few weeks. By measuring the apparent brightness of a Type 1a supernova and comparing it to the known intrinsic brightness, astronomers can calculate distances to galaxies billions of light-years away. This is how we know the distances to galaxies like Alcyonius and IC 1101. But there is another technique for extremely distant objects, and that is using redshift. As the universe expands, space itself is stretching. Light traveling through this expanding space gets stretched along with it. This stretching increases the wavelength of the light, shifting it toward the red end of the spectrum. The more distant an object is, the more space its light has traveled through, and the more redshift it exhibits. By measuring the redshift of a galaxy and using our understanding of how the universe has expanded over time, we can estimate its distance. Each of these techniques, parallax, Cepheids, Type 1a supernovae, and redshift, is calibrated against the previous one. We use parallax to measure distances to nearby Cepheids. We use those Cepheids to calibrate Type 1a supernovae. We use Type 1a supernovae to calibrate the relationship between redshift and distance. It is a carefully constructed ladder where each rung depends on the accuracy of the rungs below it. And the result is a remarkably consistent picture of the universe's structure and the distances to objects within it. But there is something else we need to talk about when discussing the scale of the universe and the sizes of galaxies. Something invisible that dominates the mass of every galaxy and shapes the structure of the cosmos. Dark matter. Dark matter is one of the great mysteries of modern physics. We know it exists because we can see its gravitational effects, but we have never directly detected it. Dark matter does not emit light. It does not absorb light. It does not reflect light. It is completely invisible to all forms of electromagnetic radiation, from radio waves to gamma rays. The only way we know dark matter is there is through its gravitational influence on visible matter. and that influence is enormous. In fact, dark matter makes up about 85% of all the matter in the universe. Normal matter, the protons, neutrons, and electrons that make up atoms and therefore stars, planets, and us, accounts for only about 15%. The rest is dark matter. In the Milky Way, the visible disk of stars and gas that we can see has a mass of about 100 billion solar masses. But the total mass of the Milky Way, including dark matter, is about 1.5 trillion solar masses. That means dark matter outweighs visible matter by a factor of 15 to 1 in our galaxy. And the dark matter is not distributed the same way as the visible matter. The visible matter is concentrated in a relatively flat disk, the spiral structure we can see. The dark matter forms a roughly spherical halo surrounding the visible galaxy. This dark matter halo extends far beyond the visible edge of the Milky Way, reaching out perhaps 300,000 light-years or more from the center. We know this dark matter halo exists because of how stars and gas move in the outer regions of the galaxy. According to Newton's laws of gravity, objects farther from the center of a galaxy should orbit more slowly, just like outer planets in the solar system orbit more slowly than inner planets. But when astronomers measured the orbital velocities of stars and gas clouds in the outer Milky Way, they found something strange. The velocities did not decrease with distance. Instead, they remained roughly constant, even far from the galactic center. This flat rotation curve, as it is called, implies that there is far more mass in the galaxy than we can see. The only way to explain the observations is if there is a massive halo of invisible matter surrounding the visible galaxy. This dark matter halo provides the extra gravity needed to keep the outer stars moving as fast as they do. The same pattern appears in every galaxy we have studied. All galaxies have flat or nearly flat rotation curves, implying all galaxies have dark matter halos. In fact, the masses of galaxies' dark matter halos are directly related to the sizes of the galaxies. Larger halos produce larger galaxies. IC 1101, with its enormous size, must have an incredibly massive dark matter halo. Estimates suggest IC 1101's total mass, including dark matter, is around 100 trillion solar masses. That is about 60 to 70 times the total mass of the Milky Way. Most of that mass is dark matter, invisible and mysterious. We do not know what dark matter is made of. The leading candidates are exotic subatomic particles that do not interact with normal matter except through gravity. These particles would have been created in the Big Bang, and they have been around ever since, forming the gravitational scaffolding that allowed galaxies to form. Physicists have built detectors deep underground and in space, trying to catch dark matter particles as they pass through Earth. So far, despite decades of searching, we have not found any. Dark matter remains elusive, detected only through its gravitational effects, but its presence is undeniable. Without dark matter, galaxies as we know them could not exist. The universe would be a very different place. And dark matter is not the only invisible component of the universe. There is also dark energy. If dark matter is mysterious, dark energy is even more so. Dark energy is a property of space itself, an energy that causes the expansion of the universe to accelerate. In the late 1990s, two teams of astronomers studying distant Type 1a supernovae made a shocking discovery. They found that the universe's expansion is not slowing down as everyone expected. Instead, it is speeding up. Distant galaxies are receding from us faster and faster. Something is pushing the universe apart, and that something is dark energy. Dark energy makes up about 68% of the total energy content of the universe. Dark matter makes up about 27%. Normal matter, everything we can see, makes up only about 5%. That means 95% of the universe is made of things we do not understand. We do not know what dark energy is. The leading theory is that it is a property of empty space itself, sometimes called the cosmological constant. But we do not know why space has this property or where the energy comes from. Dark energy is causing the universe to expand faster and faster over billions of years. This acceleration will have profound effects. Distant galaxies are already moving away from us faster than the speed of light. Not because they are traveling through space faster than light, but because space itself is expanding between us and them. As the expansion continues, more and more galaxies will cross the cosmic horizon, the boundary beyond which light can no longer reach us. Eventually, in about 100 billion years, all galaxies beyond our local group will have been carried away beyond the horizon. Future astronomers looking at the sky will see only the galaxies in our local group. Everything else will be invisible, carried away by the expansion of space. They will live in a universe that appears much smaller and much emptier than the one we see today. In a strange twist, those future astronomers might come to the same conclusion that early 20th century astronomers did, that their galaxy is all there is. Except they will be even more wrong, because there will be trillions of galaxies beyond their horizon, forever unobservable. Dark energy also affects the formation of large-scale structures. The acceleration of the universe's expansion makes it harder for gravity to pull matter together. Structures like galaxy clusters and superclusters have largely stopped growing. The ones that exist today will remain, but new ones are unlikely to form. The universe has entered a new phase, one dominated by dark energy rather than matter. Understanding dark matter and dark energy is one of the great challenges of modern physics. These invisible components dominate the universe, but we know almost nothing about them. Galaxies like Alcyoneus and IC 1101, with their enormous sizes and masses, are key to studying dark matter. By measuring how galaxies move and interact, by studying the structure of galaxy clusters, by analyzing gravitational lensing, where light from distant galaxies is bent by the gravity of intervening dark matter. Astronomers are slowly piecing together the properties of dark matter. And by studying the expansion history of the universe, by measuring distances to supernovae and galaxies at different epochs, cosmologists are probing the nature of dark energy. The largest galaxies and structures in the universe are not just impressive for their size. They are laboratories for studying the fundamental nature of reality itself. Now, let me tell you about what the future holds for our exploration of the largest structures in the universe. because the story of Alcyonius and IC1 101 is not just about what we have found, it is also about what we might find next. Astronomy is advancing at an incredible pace. The telescopes and instruments being built today will see things we can barely imagine. The James Webb Space Telescope, which launched in December 2021, is already transforming our understanding of the early universe. Webb is designed to observe in infrared wavelengths, which allows it to see through dust and to detect light from extremely distant galaxies that has been redshifted into the infrared. In just its first year of operation, Webb discovered galaxies that existed when the universe was only 300 million years old. These galaxies are smaller and more irregular than modern galaxies, representing an earlier phase of galaxy evolution. By studying these early galaxies, astronomers are learning how the first structures formed after the Big Bang. But Webb is just the beginning. The next generation of ground-based telescopes will be even more powerful. The Extremely Large Telescope, being built in Chile by the European Southern Observatory, will have a primary mirror 39.3 meters in diameter. That is almost 4 times wider than the largest telescopes currently operating. With such a large mirror, the Extremely Large Telescope will be able to collect far more light, allowing it to see fainter objects and resolve finer details. It will be able to directly image exoplanets, study the atmospheres of distant worlds, and observe galaxies at the edge of the observable universe. For galaxies like IC 1101 and Alcyonius, larger telescopes mean we can study them in much greater detail. We can resolve individual star clusters within distant galaxies. We can measure the motions of stars and gas to understand the distribution of dark matter. We can study the environments around supermassive black holes. Radio astronomy is also advancing rapidly. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the largest radio telescope ever built. It will consist of thousands of individual antennas working together, creating a collecting area of about 0.39 square miles. Hence the name Square Kilometre Array. The Square Kilometre Array will be 50 times more sensitive than existing radio telescopes. This means it will be able to detect fainter radio sources, including radio galaxies with lobes even larger than Alcyonius. It is entirely possible that once the Square Kilometre Array begins operations, it will discover radio galaxies with lobes stretching 20 million light-years or more. Alcyonius's record may not stand for long. The array will also be able to map the distribution of hydrogen gas across vast regions of the universe. Hydrogen is the most common element, and by mapping where it is, astronomers can trace the cosmic web in unprecedented detail. This will give us a much better understanding of the large-scale structure of the universe and how galaxies are distributed within it. Space-based observatories are also evolving. The European Space Agency is planning a mission called Euclid, designed to map the geometry of the universe and study dark matter and dark energy. Euclid will observe billions of galaxies, measuring their shapes and distances with high precision. By analyzing how galaxies cluster and how their light is bent by intervening dark matter, Euclid will provide new insights into the nature of dark energy and the distribution of dark matter throughout the cosmos. NASA is planning a similar mission called the Nancy Grace Roman Space Telescope. Roman will have a field of view 100 times larger than Hubble. allowing it to survey vast areas of sky quickly. It will study the expansion history of the universe, search for exoplanets, and map the distribution of galaxies in the nearby universe. These missions, and others being planned, will generate enormous amounts of data. The challenge for astronomers is not just building better telescopes, but analyzing the flood of information those telescopes produce. This is where artificial intelligence and machine learning are becoming increasingly important. Modern surveys produce images of millions or billions of galaxies. No human could possibly examine all of them individually. Instead, computer algorithms are trained to identify interesting objects, classify galaxies by type, measure their properties, and flag unusual features for closer examination. Machine learning has already been used to discover new types of galaxies, identify rare objects like gravitational lenses, and even predict the properties of dark matter halos based on the visible galaxies they contain. As telescopes get better and datasets get larger, AI will play an even more central role in astronomy. One particularly exciting possibility is the discovery of entirely new types of large-scale structures. The cosmic web, with its filaments and voids, is the largest known structure. But are there structures even larger? Some theoretical models suggest there could be. If the early universe had certain types of density fluctuations, it could have produced structures on scales larger than the observable universe. We would only be able to see a small part of such structures, but their presence might be detectable through subtle patterns in the distribution of galaxies or the cosmic microwave background radiation. These ideas are speculative, but they are being taken seriously by cosmologists. Future surveys might reveal patterns that hint at structures beyond what we can currently observe. There is also the question of what will happen to these large galaxies in the far future. We have talked about how IC 1101 grew by consuming smaller galaxies. But what happens next? As the universe continues to expand, driven by dark energy, structures will become increasingly isolated. Galaxy groups and clusters that are currently connected by the cosmic web will be pulled apart. Eventually, each cluster will be alone, separated from all others by distances that light cannot cross. Within these isolated clusters, galaxies will continue to merge. Over trillions of years, all the galaxies in a cluster might merge into a single enormous galaxy. These ultra-giant galaxies would dwarf even IC 1101. But they would be alone in an otherwise empty universe, unable to see or interact with any other structure. This is the ultimate fate predicted by current cosmological models. An empty cold universe dominated by dark energy with isolated islands of matter that can no longer communicate with each other. It is a bleak picture, but it is also trillions of years in the future. For now, we live in a universe that is still dynamic, still evolving, still full of structures forming and interacting. And we have the privilege of observing and studying this universe in real time. Every discovery, from Alcyonius to IC 1101, to the Hercules Corona Borealis Great Wall, adds to our understanding. Every new telescope, every new survey, every new technique reveals more about the cosmos. We are living in a golden age of astronomy, The pace of discovery is accelerating. Questions that seemed unanswerable a generation ago are now being addressed. And new questions are emerging. Questions we did not even know to ask. What is dark matter made of? What is dark energy? How do supermassive black holes form and grow? Are there structures even larger than the Hercules Corona Borealis Great Wall? Is life common in the universe, or are we alone? These are the questions driving modern astronomy, and while we may not answer all of them in our lifetimes, we are making progress. Each discovery brings us closer to understanding. The biggest galaxy we have discovered, Alcyonius, is not just a record to be broken.
It is a window into the physics of supermassive black holes, relativistic jets, and the intergalactic medium.
IC 1101 is not just a giant collection of stars. It is a laboratory for studying galaxy mergers, dark matter, and the evolution of elliptical galaxies. These objects are teaching us about the universe, and the more we learn, the more we realize how much we do not know. That is the nature of science. Every answer raises new questions. Every discovery reveals new mysteries. And that is what makes it so exciting. We will never know everything. The universe is too vast, too complex. But we can keep learning, keep exploring, keep pushing the boundaries of human knowledge. And as we do, we will discover things that amaze us. We will find structures larger than Alcyonius. We will understand dark matter and dark energy. We will answer the big questions, and we will ask new ones. That is the future of astronomy. That is the future of human exploration.
Not exploration with spacecraft, at least not anytime soon, but exploration with telescopes and computers and human minds, reaching out across the cosmos, studying the largest structures, understanding how they formed and how they evolve. And through that understanding, comprehending our own place in the vastness of space. Let us talk about what all this means. Why does it matter that Alcyonius has radio lobes stretching 16.3 million light-years? Why should we care that IC 1101 contains 100 trillion stars? On one level, it matters because it teaches us about how the universe works. These enormous structures tell us about the power of supermassive black holes, about the properties of the intergalactic medium, about how galaxies form and evolve over billions of years. But on another level, it matters because it puts our place in the universe into perspective. For most of human history, we believed we were at the center of everything. The Earth was the center of the universe, and everything revolved around us. We were special, central, important. This view was shattered step by step over centuries. Copernicus showed that Earth orbits the Sun, not the other way around. Galileo's telescope revealed that other planets had moons, that the universe was larger and more complex than anyone had imagined. Hubble proved that the Milky Way was just one galaxy among many. And now we know that the Milky Way is not even a particularly large galaxy. It is comfortably above average, sitting in the top 5% of galaxy sizes, but it is dwarfed by supergiants like IC 1101. And even IC 1101 is tiny compared to structures like Laniakea or the Sloan Great Wall. We are not at the center of anything.
we are not special in terms of location or scale. Earth is a small, rocky planet orbiting an average star in the outer regions of a large, but not exceptional, spiral galaxy.
That galaxy is part of a small group of galaxies on the outskirts of a supercluster, which is itself part of larger cosmic structures. At every scale, we are ordinary. And yet, despite this ordinariness, despite our cosmic insignificance, here we are, conscious beings, aware of ourselves and our surroundings, capable of studying the universe and understanding our place in it. We can measure the distance to galaxies billions of light years away. We can calculate the size of structures so large that light takes millions or billions of years to cross them. We can piece together the history of the universe from the Big Bang to the present day. That is remarkable. The universe does not care about us. The enormous structures we have been discussing, Alcyonius and IC1101 and Laniakea, they exist completely independent of whether we observe them or not. They would be there whether we existed or not. But we do exist. And we have built telescopes and developed theories and conducted observations that allow us to see and understand these structures. We are the universe looking at itself. We are a tiny part of the cosmos that has become aware of the whole, and that is something worth appreciating. Yes, we are small. Yes, the universe is vast. But we are here. We exist against all odds on this small planet in this ordinary galaxy. Life arose. Not just life, but complex life. Multicellular organisms, animals, eventually humans. Conscious beings capable of looking up at the night sky and wondering what is out there. We build telescopes to see farther. We develop mathematics to understand what we see. We send probes beyond our solar system, carrying messages from humanity into the cosmic ocean. We are the universe's way of knowing itself. We are a small part of the cosmos that has become aware of the whole. And that is extraordinary. The fact that we are small does not make us insignificant. If anything, it makes our existence more remarkable. Against the vast emptiness of space, against the overwhelming scales of galaxies and superclusters, here we are, a tiny island of complexity and consciousness in an ocean of mostly empty space. So yes, Alcyonius is enormous. Its radio lobes stretch for 16.3 million light-years. IC1101 contains 100 trillion stars. The Hercules Corona Borealis Great Wall spans 10 billion light-years. These structures dwarf the Milky Way, and they dwarf Earth even more completely. But they also make what we have here even more precious. As far as we know, Earth is the only place where life exists. We've searched for signs of life on other planets, and we have found nothing conclusive. We have listened for radio signals from other civilizations, and we have heard only silence. Maybe life is common in the universe, and we just have not found it yet. Maybe it is rare, and we are alone, or nearly so. We do not know. But we do know that life is here on Earth. And that makes this small planet orbiting an average star in an ordinary galaxy incredibly special. Not special in terms of size or location, but special in terms of what it contains. Life, consciousness, art, music, love, curiosity. The capacity to wonder about the universe and our place in it. Those things do not depend on size. They depend on complexity, on organization, on the remarkable fact that matter can arrange itself in ways that give rise to thought and feeling. Size does not determine significance. Alcyonius is enormous, but it is not aware of its own size. It does not know it exists. It does not wonder about its place in the universe. We do. We are smaller, but we are conscious, and that makes all the difference. The universe gave us this gift: consciousness, curiosity, the ability to wonder. Make the most of it. Keep looking up. Keep asking questions. Keep learning. Because that is what makes us human. That is what makes us special in a universe full of giants. The biggest galaxy we have discovered is bigger than your imagination. But you are remarkable too. The fact that you exist, that you can think about these questions, that you can feel awe at the scale of the cosmos, that is just as extraordinary as any giant galaxy. The universe is vast, but it is also beautiful, and you get to be part of it, if only for a brief moment in cosmic time. That is a gift. Make the most of it.